We have completed one problem in the previous video. So in this previous video I told you that S is equal to 36 and S is equal to 54, both satisfy the limitation. So from that, which one I have to select? But in the previous problem I completed using this, but why I am selecting this value though these two values are satisfying the condition? Okay, so just I explain. ZS is equal to total number of conductors per slot is equal to 1452 divided by 36 40, and 54 divided by 54 is equal to 27. Okay, so in this one, the third point, if you are seeing that previous videos, selection of stator slots, there are 4 conditions. That fourth condition is it should not exceed this slot loading. The values should not exceed the slot loading, correct? Now I want to find out the slot loading. Slot loading nothing but ZSS multiplied by IZ, current flowing through the conductor multiplied by number of conductors in a slot. Okay, so 40, for example, we are selecting the first case 1, that is S is equal to 36, and S is equal to 36, ZS is equal to 40. I have calculated here. Okay, at that time the slot loading is equal to 487.32. Clear? So I want to find out the slot loading for this case. So slot loading is equal to ZSS multiplied by EZ. So ZSS here 27 multiplied by phase current 12.183. At the time still the value is minimum. So 328.941. Okay, so there are two values. From this we want to select any one particular value. Normally the slot loading should not exceed 750 ampere per conductor. Not per conductor, ampere conductors, like MMF. Slot loading should not exceed the limit 750 ampere conductors. So both the values, here it is 487.32, here it is 328.941. Both the values are very less, but it can go up to 750. So the nearer value is 487.32. This is still very less, but here this is towards 750 ampere conductor, so I can select this value. So this value is related to 40 is related to 36. That's why in the previous problem I have selected this 36. Hope you would have understood this. Now I am going to start this next topic in this chapter. Dear students, in this video I am going to continue with the next topic, design of wound rotor, that is slip ring rotor. This covers the lecture number 46 to 49. Okay, so you know about slip ring induction motor, just you are adding external resistance, correct? So by varying the external resistance you can able to improve the torque developed by the motor. So this rotor is made up of laminated core and semi-enclosed slots, and also it consists of 3-phase winding. In your squirrel cage induction motor it consists of bars, but for your slip ring induction motor it consists of 3-phase winding. This diagram represents your slip ring induction motor. The slip ring induction motor rotor consists of 3 windings R, Y, B. So it may be connected in star, otherwise delta. Here star connection. See here, the center part is connected together, and this orange color represents the shaft of the motor. Orange color represents shaft, and the next end of the winding is connected with slip ring. So these are all, this violet color represents your slip ring. This violet color represents slip ring. Okay, so with this slip ring the windings are connected with the slip ring. The slip rings are connected with your external resistance. Slip rings are connected with external resistance. So while you are varying this resistance, automatically here you are changing this RYB resistor, so automatically it will affect the torque of the motor. Correct? This is actually your diagram here. Now we want to find out some design values for your rotor. So first one, you want to find out number of rotor turns. Similar to your stator turns TS, here you are going to find out TR. So rotor is like a secondary of transformer. I told you that the induction motor is called as rotating transformer. It consists of primary winding in the stator, secondary winding in the rotor. Also, you want to consider voltage between slip rings. So between the slip rings, what is the voltage you have to consider? It should not exceed the limit. It should not, because you are connecting the resistor, automatically it will the voltage between the two slip rings will also be varied based on the resistance values. So it should not exceed the limit. For the small motors, it should not go beyond 500 volt. For the large, it may go up to 2000 volt. That we have to remember. Then I want to find out induced EMF in the rotor winding. ER I have to calculate. This is induced EMF in the rotor from stator. As it is a transformer, I am using a transformation ratio K, that is ER by ES, secondary induced EMF divided by primary. It's a rotor EMF divided by stator EMF, that is equal to, this is a constant, KWR TR divided by KWS TS. So turns, number of turns in the rotor, number of turns in the stator, this represents the constant. So rotor turns per phase is equal to, I want to calculate this. So TR is equal to, just rearrange everything, you can get this expression. I want to find out rotor ampere turns. Normally rotor ampere turns is 85% greater than stator ampere turns. So 0.85 into stator ampere turns. So rotor ampere turns ultimately MMF. So current flowing through that rotor multiplied by number of turns per phase in the rotor, that is equal to 0.85. Current flowing through the stator, number of turns in the stator, everything is represents a phase values. So I am calculating IR, that is equal to, rearrange, you can get this expression. So for the rotor, the current density you have to assume 3 to 5 ampere per meter square. For the stator also, it should be in this limit, 3 to 5 ampere per mm square. So area of the rotor conductor AR is equal to IR by del R. So here the number of rotor slots should not be same. So dear students, number of stator slot procedure, here the procedure similar to the number of stator slots. You want to select the number of rotor slots, you have to follow the procedure which is same as that of number of stator slots. It's not numbers, the values are not equal. Here I have given the procedures are same. Yeah. Then we have to find out some other data also. So rotor core details, depth of rotor core DCR. Depth of rotor core means, see this diagram. So this represents a rotor. The rotor consists of a semi-enclosed slots. See here, this the diagram. So in this it represents DCR core. This represents core. So like that, it is connected. Like this. So this portion represents the core, rotor core diameter, and then it represents DSR, that is slot diameter, not diameter, depth. DSR nothing but depth of rotor slot, DCR nothing but depth of rotor core. DCR represents depth of rotor core, this represents, this portion is core, and then this is DSR nothing but depth of rotor slot. So R represents rotor, S represents slot, here C represents core, D represents depth. Okay, so DR represents the diameter of the rotor, full diameter, and DI, this is DI, this is inner part has insulations, so or laminations. So this portion is DI. So we want to find out DI. DI is equal to full DR minus this and this on both sides. So DR minus 2 DSR plus DCR. And I can calculate DCR. DCR is equal to 5M divided by 2 DCR multiplied by LI. This is, I am calculating from BCR is equal to 5M divided by area of the rotor core. Okay. So instead of ACR, I am substituting 2 DCR LI. By rearranging this, I can get this expression. So we want to find out the details about the slip rings and brushes. So the first one is slip ring. The slip ring, already I have drawn one diagram. Remember the diagram. The slip rings are mounted on the shaft. and it's made up of brass or phosphorus bronze. So the size shape of the slip ring is rectangular shape. I want to find out the area of slip ring. Same formula, current divided by density. For the slip ring, the density varies from 4 to 7 ampere per mm square. The brushes are made up of metal graphite. It is made up of alloy of copper and carbon, which has very low resistance and high mechanical strength. The current density of this is 0.1 to 0.2 ampere per mm square. These values you have to remember. So this value is very less when comparing to all the previous values. Next one is dispersion coefficient. So it is a ratio of magnetizing current to short circuit current. So this is dispersion coefficient represented by this sigma. If it is high, it will affect the power factor. So this value, you have to select this value correctly. That is, this is a ratio of Im by short circuit current, stator current. Okay, so short circuit current. PF, if you are selecting this value, high value, it will produce as poor power factor, and overload capacity is also reduced and output is also reduced. So you have to use this expression to find out dispersion coefficient. You have to find out these values using ISCI, that means short circuit current, ideal short circuit current. This is equal to phase voltage divided by total reactance, leakage reactance of the motor referred to stator. Total leakage reactance is like a transformer, so all the primary and secondary should kept in one side. So you have to find out the total leakage reactance. The next video we will discuss about the problem.